So a singularity, or singular point of a function phi of z, is any point at which phi of z is not analytic. So a singular point is said to be isolated if it's the only singular point within a small circle. So most singularities, or the singularities you're going to meet as physicists are always going to be isolated. It's actually quite difficult to come up with singularities which are not isolated. Just for fun, you can consider this example. The function 1 over sine 1 over z has a singularity at z equals 0, which is not isolated. You just have to think what this function actually looks like. Well, sine of 1 over, well, you know what sine x looks like. So sine of 1 over x, the oscillations get faster and faster as you go to 0. Okay, so it crosses, so if we're just talking about sine of 1 over x, it crosses the x-axis faster and faster. So the zeros get closer and closer as you as you x tends to 0 without limiting. Which means that when you take 1 over, you're getting singularities which get closer and closer without limit. So you can't possibly draw a circle around x equals 0 without including an infinite number of other singular points. Okay, but anyway, as I said, this is not a function you're going to meet in physics as far as I know. Right, so suppose phi of z is an isolated singular point. So it has an isolated singular point at z equals z0. Then near, but not actually at the point, it's possible to express phi of z using what's known as the Laurent series for phi of z around z0. So this is a generalization of the Taylor series. So this thing here, the A0, A1, A2, and so on terms are the Taylor series. To the Taylor series, to cope with this singularity at z equals z0, we add these extra terms here. Okay, so you can obviously see that when z equals z0, these go to infinity. But these are enough to represent what we need to know about what happens close to z0. And we classify an isolated singular point according to the values b1 and b2 take, or specifically whether the bi are 0 or not. If b1 is not 0, but all of the other b's are 0, then we call it a simple pole. If bm is not 0, but b sub j, where j is greater than m, are all 0, then we call it a pole of order m. So this is very similar to our definition of a 0 of order m. I mean, it's sort of basically converse to it. Finally, what happens if there's infinitely many b's, well, okay, which are not 0? Then we call z0 an essential singularity. So basically, if the b's, that you can always find a bm for any for large, well, okay, yeah, there's going to be an infinite number of b's which are not 0. Finally, there's one type of singularity which in a way is not a proper singularity. Okay, and that's when if f of z is actually not defined at z0, but if you take the limit of fz as z tends to z0, then the limit exists and is finite. Then we call z0 a removable singularity, or we say the function has a removable singularity at z0. So an example of this is the function sine z over z. Now, strictly, this doesn't exist at z equals 0 because you're dividing 0 by 0. But as you probably know, or if you apply L'Hopital's rule, then the limit as z tends to 0 of this function is 1. So the limit is defined as z tends to 0, and so we therefore call this a removable singularity. We say as z equals 0 as a removable singularity. So technically it's a singularity because the function is not defined, but it's just a nice sort of singularity in that it doesn't go to infinity. So remember that this is important, that you realize that a removable singularity is sort of like a friend. It's something you don't have to worry about effectively when we do the calculus of residues, but more on that later. So it's actually often just like it's when you actually, if you do question 14 or studied this, it's not actually necessary to use this definition of what the order of the zero is. You don't have to differentiate m times and check when it's 0 to actually work out what type of zero you have. It's much simpler just to observe that your function is several functions which are simple zeros multiplied together, and therefore you can work out the order by using this result here. The same goes for singularities. So it's often basically not necessary to actually write out the Laurent series to classify singularity. So to start with, if z0 is a singular point of fz, then it's going to be some type of pole if f of z tends to infinity. The modulus of f of z tends to infinity as z tends to 0. So that means it's a pole rather than an essential singularity. Otherwise, if there's no limit, if you can't work out what the limit is going to be, then it's an essential singularity. Also, rather than using this Laurent series, you can actually just use this result here, that f of z has a pole of order m, if and only if we can write this down, where g is not 0 at z0. Or sorry, not 0, is analytic at z equals z0, is also not 0. So using this result and comparing it with 2.7, hopefully it's fairly obvious that if this following sentence, that 1 over f has a pole of order m at z equals z0, if and only if f of z, without the 1 over, has a 0 of order m at z equals z0. So you can sort of think of a 0 being the opposite of a pole, and you can sort of think of, if you like, a 0 of order negative number. If I allow this m to be negative, then it becomes a pole of order minus m. If I allow this m to be negative, then it becomes a 0 of order minus m. So they're converse of each other. Which makes life simple when you're trying to work out what type of singularity you have. So if you understand how to get the order of a zero, then you should be able to understand how to get the order of a singularity. They're just converse of one another. Okay, so now we can generalize this sort of product formula we had here to cope with singularities as well. So suppose Fi and Gj have zero of order mi and poles of order nj at z0, and we define p by summing up the orders of the poles and then subtracting the orders of the zeros. Then if p is greater than 0, so the poles win, then it has a pole of order mod p at 0. If p is less than 0, that means the zeros are winning when we multiply all these functions together. Then we end up with a 0 order mod p at z0. Then I've asked what happens if p equals 0. Well, you can think about that. Okay, well, the answer is that you get a removable singularity if p equals 0. Okay, so as I sort of hinted, poles and zeros are mutually inverse in the sense that a pole of order m can be thought of as a 0 of order minus m, and vice versa. A 0 of order m can be thought of as a pole of order minus m. Okay, I don't think you have to really worry about this next sentence. Okay, so then we're going through a few examples. Check through the following examples.